So today we are going to discuss interacting classical gases. So this will be somewhat phenomenological. So, so far we've been ignoring interactions. Even when we looked at the diatomic gas, we didn't really consider the interaction between different molecules, right? So experimentally, as we saw, the ideal gas law, which results from ignoring interactions, is only valid for low densities. So we can think of the ideal gas law as being the lowest order term in an expansion in terms of an expansion parameter, which is n over v. So n over v is a small number. So we want to, in a suitable units. So we want to expand our expression for pressure as a function, as a power series in n over v. So we want to take an ansatz. So the ansatz is really not an ansatz, but more of a, we can always do this. So the pressure over kBt, the leading term is going to be n over v. And then there will be terms such as B2. This is a coefficient we have to figure out. N squared V squared. And then B3 N cubed V cubed plus dot dot dot. The more terms you include, the more accurate your gas law will be. For this lecture, we'll just be content with figuring out B2. Okay, and that will give us the van der Waals gas. So we are essentially expressing pressure as a power series. And this expansion is known as the virial expansion. And these coefficients are known as the virial coefficients. Okay. So this is the setup for the interacting classical gas, analysis. So to determine B, or the virial coefficients, we need to know what the interaction potential is between two gas molecules. And that comes from fundamental physics. And you can get as original or as, ab initio as you want. Ab initio means from initial consideration. So for example, you can start with a quantum mechanical Schrodinger equation, and you can solve the Schrodinger equation and figure out what the interaction between two gas molecules is, or you could have like a more of a hand waving picture, and then try to figure out, see, and have some sort of comparison with experiments and see if that works. So here we are going to be very, very hand waving. Okay, so we are going to work out what the interaction potential is. So, we are dealing with chemistry essentially, right? Because we're dealing with the interaction between molecules. So we are kind of, in the regime. So the only interaction here between, it can be just electromagnetic interactions. So we are considering the electromagnetic interactions between, say, two electrically neutral atoms. So how do electrically neutral atoms interact with each other? Does anyone have any idea?
Sometimes they can have temporary dipoles because of the aligning of electrons and stuff.
Right.
That's what I learned in chemistry.
Yeah, exactly. The chemistry told you right. So essentially, what happens is that, what is the atom like? An atom has some positive nucleus. Of course, because of quantum mechanics, this is not extremely well defined, its boundaries, but some charge, positive charge, and it's surrounded by a cloud of negative charge electrons, right? And this is negatively charged electrons. And because of the fact that the electrons are whizzing around, and their probability, so there will be temporarily there is going to be in the separation of charges, right? And there is going to be temporarily some induced, not induced, some because of the quantum fluctuation, there will be some time-dependent dipole moment. Okay. Now, if there's a dipole moment in physics 2, in 112 or whatever equivalent course you took, you learned that the dipole moment, the modulus of the dipole moment, if it's P1, then it's going to have an electric field which is going to fall off as 1 over r cubed, where r is the distance from the dipole. Okay, if it's a small dipole, so if it's a dipole like this and this is r, then the dipole moment is going to, the electric field is going to fall off as 1 over r cubed. So that's interesting because even though the dipole is an electrically neutral object, because the two charges are not coincident, it still has an electric field. Now, if you bring another atom within this electric field, so suppose that there is an atom over here with its own cloud of electron around it, then this electric field is going to induce a dipole moment in that atom. And so if that dipole moment in that atom is P2, it's going to be proportional to the first electric field, which is P1 over r cubed. And if you work out the potential energy, and I'm sure it's somewhere there. Well, I don't think it's ever taught in physics 112, but the potential energy of this configuration, this temporary configuration, will be P1, P2 over R6. Okay? And so this is going to be an attractive potential. Now, suppose that the two atoms are very close to each other. They come very close to each other because they're attracted. Then what's going to happen is that their electron clouds are going to start overlapping. But electrons are spin half particles. That means electrons have intrinsic spin, which is half times h bar. So this is the electron spin, okay? In other words, electrons are fermions. So fermion starts with small f. So in quantum mechanics, there is a principle called Fermi's exclusion principle. Which says that the two fermions with the same quantum numbers cannot coexist in the same location.
Isn't this Pauli's exclusion principle?
You're very right.
We are taught it as Pauli.
Yeah, you're right, Pauli. Sorry. I'm sorry. Yeah, I should not have. I don't know how I forgot that. Yeah. Sorry. Yeah. The statistics is by Fermi, but the principle is by Pauli. Yeah. Thank you very much. Yeah. Pauli was a very interesting guy. So was Fermi, but Pauli was more interesting than Fermi. Pauli probably caused Professor Abdus Salam to miss a Nobel Prize. When Abdus Salam was a young physicist, he came up with an idea about parity violation and neutrinos, about some missing energy problem in neutrino physics, and he proposed the idea of parity violation. But he made the mistake of sharing the idea with Pauli before publishing it. Pauli scolded him for how terrible the idea was and told him to think of something better. So Salam never published it. Yang and Lee published the same idea and got the Nobel Prize as a result. So because of that experience, Abdus Salam published everything else in his life. He said that whatever idea he had, good or bad, I just published it. Anyway, so Pauli was a very, very intimidating and very famous figure in theoretical physics. Okay, so because of Pauli's exclusion principle, there is some kind of very natural repulsion between atoms. Okay? When they're too close to each other. Now, we don't really care what this particular form of this repulsion is. So what we are going to do is that we are going to just approximate that. You can do it in various forms, and there are, I think these are called the Lennard-Jones potential. And the idea is something like, you take U of R, which is the potential between, two molecules, and at very short distances, you have a repulsive potential because of the plus sign. And at greater distances, you have an attractive potential. What matters is, this exponent, which is motivated by the consideration of magnetic of the electric dipole. But here, this 12 is chosen so that when you're doing the mathematics, because 12 over 6 is a nice number, it works out. So that's used often, but we are not going to use that. We are going to use a different kind of potential, which is, I think it's known as the hardcore potential. And the hardcore potential is something like U of R becomes infinity at R less than R0, and it's minus U naught R naught by R to the power 6 for R greater than or equal to 0. Okay, so the second potential looks something like this. So this is the
Sir, what is R and R naught?
yeah, I'm coming to that. Yeah. So this is the distance. So this is U of R. R is the distance, radial distance from the core of the atom. So if your atom is like this, then this distance is R. And R naught is this distance. R naught is essentially where the equilibrium point is. Okay? So this actually does like this. So this potential is easier to calculate because this integral is much easier to calculate. Okay. So we'll actually be using this one. And you can also, alternatively, you can use a potential which is a little bit more realistic. Say, they all give you more or less the same qualitative answer.
So they're like different approximations?
Exactly, yeah. So there's another one where, you have a little bit of a, so this is something that we like in quantum mechanics very much, this sort of piecewise piecewise linear potentials, because, you can do all the integrals exactly in this case. Okay, so this is another one. But for this purpose, for the purpose of this lecture, we are going to take this potential. As I'm following David Tong, David takes this potential, okay? But if you look into Salinas, Salinas uses this potential. All right. So, any questions?
So these are what we are referring to as interacting potentials?
Yeah, exactly. So, I mean, if you look at this first potential, this guy, let me just sketch it. The first potential will have a much nicer form than the others. But it's harder to calculate with. So it'll be something like this, right? And this point is going to be R0.
So in the square-shaped graph, where is R and R naught?
Yeah, that's a good idea. You can take R naught to be this. And R is just a variable. This is R changes.
So how does that square graph work? I mean, there is a straight line beside R naught on left and right. So
right, when you do the integrals, when you're doing an integral over this graph, your integral has something, say u of r, right? And d of r, and say 0 to infinity. So then in this case, what will happen is that this integral will just break up into two integrals. One will be from, okay. What you'll have is that here you will have, actually, no, okay. Because of the partition function, the integral will be of this form. You'll have to do e to the power minus beta, then u of r. Okay, so when you do the integral from 0 to infinity, what will happen is that the contribution from this part is going to vanish, because that's going to give rise to 0 here, right? So this integral will become an integral. I think so. Let's call this, say, R1, and let's call this R2. Then this integral will become something from R1 to R2, and then R1 to R2 will have, say, A, and then you will have e to the power minus beta, and then you will be minus whatever the depth of this thing is. Suppose it's u naught, so it's going to be plus of u naught d of r, and then there's going to be another integral from R2 to infinity. There will be e to the power minus 0, which is 1, then there will be, say, okay, there will be other factors here. And
so this is for the calculation.
Yeah.
Okay.
Yeah, when you do calculations like this is how you break up integrals. And the idea is that because every integral is now an integral over constant factors, therefore it's very easy to do these integrals. Whereas for these kind of cases, your integrals become integrals over functions. Therefore, it's harder to do the integrals. You can still do them numerically sometimes exactly. Sometimes you can do approximations. In physics, we can hardly ever solve a problem exactly, and this is a case, a simple example of this case. It's not, you can still solve this problem exactly. Like if you take this integral, you can use some very fancy hypergeometric function. You can use some, fancy mathematics and solve it. But are you getting a lot of physics out of doing that fancy mathematics? The answer is no. So the physics you need is good enough if you use this approximation. And that's what we're going to do, okay? If you are going to, say, publish a paper that's going to do very, compare with very precise experimental data, you can do a very precise calculation. But for our purposes, we don't have to.